Hello everyone. Today I will present to you our paper Coordinated Control of UAVs for Human-Centered Active Sensing of Wildfires. This paper is accepted to American Control Conference 2020. I am Esmaeil and this work was done in Core Robotics Lab at Georgia Tech with my advisor Professor Matthew Gombolay. Wildfires are destructive and inflict massive irreversible harm to lives and natural resources. According to the Insurance Information Institute and U.S. Fire Administration, more than 245,000 wildfires burned more than 30 million acres, destroyed about 30,000 structures, and took away hundreds of human lives, causing a total of more than $53 billion in damage. And this is only for the last 4 years. Firefighters need online and dynamic observation of the firefront to anticipate a wildfire's unknown characteristics, such as size, scale, and propagation velocity, in order to plan their strategies accordingly. And so, due to recent advances in aerial robotic technologies, teams of autonomous UAVs have been proposed as a solution to provide firefighters with real-time fire monitoring information, mainly because of their agility, cost efficiency, and hovering capabilities. Firefighters need frequent high-quality images of the wildfire to make strategic plans. There's a large body of literature dedicated to studies on autonomously surveilling large burning areas by drones through various vision-based, fire intensity-based, or even data-based approaches like reinforcement learning. Many of these studies, however, require a fire shape function or an accurate estimate of maximum heat intensity within the entire fire map, which are non-trivial and in some cases even non-realistic. Moreover, our RL-based approaches also suffer from major drawbacks such as scalability and lack of formal guarantees on the boundedness of errors, which are in fact significant for safety-critical applications. Nevertheless, these are not our only motivations here. There is a clear absence of human-centric approaches in the autonomous multi-agent fire monitoring literature. This is mainly because a majority of previous studies are solely focused on fire detection or surveilling a large burning area rather than focusing on local human-defined areas of priority. Firefighters may easily lose their lives as a consequence of inaccurately anticipating information due to low-quality information provided regarding their time-varying proximity to a fire. Here, to give the information quality a better sense, by high-quality information, we mean local, high-resolution images or other sensory information in that sense that are captured from a close-by distance with respect to the areas prioritized by humans. Here, we propose our distributed control framework for human-centered active wildfire monitoring. In our approach, we propose a dual-criterion objective function based on Kalman uncertainty residual propagation and multi-agent consensus protocol, which enables the UAVs to cooperatively track and monitor the fire transition and provide safety information for firefighters on the ground using the acquired information. Here, Q and P are discretized fire and UAV positions, U is a measurement uncertainty map, and E is the total displacement energy among all networked UAVs. And specifically, in the first component of our objective function, UAVs try to minimize the measurement uncertainty by flying around a combined uncertainty map made up of both wildfire propagation areas as well as areas of human operation. We also incorporate a formation controller in the second term of our objective function to encourage the UAV team to maintain a formation consensus for maximizing the coverage. Maximizing this dual criterion objective function generates the virtual next position PV for each UAV at node level, which is then fed into a path planning controller to generate the driving forces. But before diving into the details of our controller, let me introduce the Farside fire propagation model. The Fire Area Simulator, or Farside Wildfire Propagation Model, was first introduced in 1998 and is now widely used by the USDA National Park Services, USDA Forest Services, and other land management agencies at the federal and state levels in the United States. It uses a numerical motion model for fire spot Q at time t, in which Q dot is the fire growth rate, which is a function of three essential environmental parameters, RU and theta, that represent fuel or vegetation coefficient, mid-flame wind speed, and wind direction, respectively. The first component of our controller is the uncertainty control component. Here, we wish to create an uncertainty map that is reflective of the fire dynamics and UAV state estimation error. We leverage the extended Kalman filter for this purpose, in which the transition and observation equations can be formed as shown. The state vector S includes variables Q as location of the fire spot, P as the UAV position, and far-side model parameters RU and theta introduced in the previous slide. The state vector is multiplied by the transition Jacobian matrix, which includes the gradients of the far-side model M with respect to the state variables, and the result is summed by the process noise, omega, which here is modeled as a white Gaussian noise. This process updates the current state estimate for time t, which is then fed into EKF's observation equation in order to map the status space to observation space and obtain the state estimates as observed by a flying UAV sensor. While I do mention that here OT represents a flying UAV's observation model of a dynamic fire spot on the ground as shown in this figure, please refer to our paper for more details on these derivations. Now, we can use EKF's measurement error residual to propagate the uncertainty about the estimated state variables and accordingly generate a fire uncertainty map. Here, capital P is the state covariance and capital F is the transition Jacobian matrix as introduced in the previous slide. Also, QT is the process noise covariance. The state covariance P is multiplied by H, the observation Jacobian matrix, and its transpose, and the result is summed by the observation noise covariance to obtain the capital S as the prediction variance. This prediction variance is then used to create our first objective function, the fire uncertainty minimization objective, in which to minimize the measurement uncertainty, we try to maximize the prediction variance S. But what does it even mean to maximize the prediction variance? For intuition, let's look at it this way. If you are uncertain about an information, say the notes on a sign you're trying to read in a distant location, you get close to have more accurate and higher quality information. This is exactly the idea behind our uncertainty-based controller, which means a maximally informative position for a drone is the one that minimizes the HH transpose multiplication in the prediction variance equation, or in other words, the closest possible position where dynamic observations change rapidly. Technically, assuming two fire spots that one is closer to our UAV sensor than the other, with the exact same observation angle error, the estimation error associated with the farther point is much greater than the estimation error of the closer point. Therefore, we try to minimize our estimation error or uncertainty by trying to get close as possible to the target points. As such, our objective function enforces the UAVs to fly to locations with higher uncertainty, which then leads to lowering their uncertainty as UAVs get closer. Now, let's hold on to this fire uncertainty map. As I mentioned earlier, we also create a human uncertainty map to be combined with the fire uncertainty map. As shown in this slide, while hovering around the highly uncertain areas, UAVs are required to focus on their human collaborators on the ground as well and take their safety into account by putting additional concentration on the areas of human operation. So UAVs receive human positions, for instance, through GPS devices, and generate a bimodal Gaussian distribution to account for both GPS error as well as mobility of the humans. The second component of our controller is the formation control component, to ensure that the combination of our uncertainty objective functions results in local actions leading up to appropriate global performance. We enforce this extra control module in such a way that the UAVs also act on other easily measurable information, such as the relative distance to neighboring drones. This is specifically important to disperse UAVs from converging to an extreme minima, like a highly uncertain point, while preserving the connectedness of the network. To this end, we leverage the weighted multi-agent consensus protocol with an energy function as presented with the objective of minimizing the total displacement error E, while preserving a distance of at least a small delta between all UAVs with maximum communication ranges of capital delta. In this way, a negative force will be generated to move UAVs apart from or close to each other if they are getting closer than a small delta or farther than capital delta. Next, to calculate the driving forces generated by the uncertainty and formation control components, after combining the two fire and human uncertainty maps, we calculate the negative gradient of the total uncertainty energy with respect to the drone's position PD along X, Y, and Z directions. Same is repeated for the formation control component that generates the second driving force. Here, the kappa 1 and 2 are the respective gain coefficients for uncertainty and formation controllers. Next, we combine the two forces to generate the next virtual position, or a potential goal, for each drone D, which is then fed into an artificial potential field-based path planning controller to generate the final control input UD for each drone. The path planning controller can generate a set of attractive and repulsive forces to move the robot towards its next virtual position, or to avoid undesirable poses, such as altitudes too high or too low. And eventually, the final control input results in a position update for each drone D, as shown here. This figure shows the simulation results of 8 sample time steps between time 20 and 300 seconds, where squares are drones' respective fields of view projected on the ground. The simulation parameters in our empirical evaluations are shown in the table. As shown in our simulation results, UAVs start from a distant location and move towards the locations where there's uncertainty about their estimation in order to have better estimation and therefore lower their uncertainties. Eventually, as shown, after 5 minutes of running the simulation, we can see that the UAV team can distribute effectively and cover the wildfire area to reduce their measurement uncertainties. We also evaluated the efficiency of our controller for distributed coverage tasks against 2 benchmarks: a state-of-the-art model-based distributed control algorithm and a deep reinforcement learning baseline. The first benchmark is a fire heat intensity-based distributed control framework for wildfire coverage, which incorporates an artificial potential field-based controller. For the RL baseline, we trained a policy network to control UAVs. We ran the simulations for 100 time steps for all 3 methods for a total of 10 trials, where for each trial a cumulative uncertainty was calculated by the EKF for fire points not covered by any drones at each time step. While the RL baseline failed to learn a useful policy during 1,000 episodes of training, our approach shows significant improvements by reducing the cumulative uncertainty residual by more than 10 to the power of 2 and 10 to the power of 5 times the other 2 benchmarks. In a later study, we also implemented a deep reinforcement learning benchmark approach specifically proposed for wildfire coverage and evaluated its performance in our environment, which, as presented in this figure, our approach again outperforms the benchmarks in reducing the total measurement uncertainty. As a corollary of our algorithm, we leverage the estimated fire model parameters RU and theta and calculate an individualized safety index SI as a temporal quantity by taking into account the velocity and direction of the approaching firefront, and report this quantity to firefighters for situational awareness. Here, PIH is a cumulative distribution that predicts the probability of fire spots moving inside a circular vicinity with radius RS of the human firefighters. Therefore, we note that this safety index is basically a time index that shows a probabilistic measure of how long it is left before fire gets too close to firefighters. An important note about this individualized safety index is that it can be used as a weighting coefficient when scaling and combining the human and fire uncertainty maps to prioritize among firefighters. This figure shows the variations of our temporal safety index with respect to distance between an approaching firefront with 10 points and a firefighter. The safety index can be used by human firefighters to define some TS and TW as temporal bounds for safety and warning situations. But please note that these bounds are left to be defined by humans, since they are subjective to the firefighting scenario and are dependent on situational severity. For example, a wildfire approaching a hospital versus a forest fire. We also evaluated the feasibility of our method on physical robots. We implemented a distributed controller on 5 robots in a multi-robot testbed. Robots were tasked to cover a simulated wildfire while focusing on the activity areas of 5 simulated moving firefighters. Note the swarm-like behavior of the robot team as a result of our combined formation controller and uncertainty controller, which through a combined uncertainty map enables robots to monitor the wildfire propagation while also effectively focusing on the areas of human activity. Also, this video is uploaded on YouTube and it can be searched. And with that, I finish my presentation. Thank you very much.